Number 73. Which of the following structures would you expect for nitrous acid? And then determine the formal charges. And then they give us two depictions of what nitrous acid would be. It could either be this drawing or it could be this drawing. Now, technically, we don't really need to know which one of these is nitrous acid by the formal charges. I'm going to give you a little secret, right? Now, we've learned about electronegativity, right? I think that was last chapter. Remember, electronegativity, the more electronegative an element is, the more it's going to be greedy and pull the shared electrons closer to that atom. And we should know the trend, right? As we go from left to right across a periodic table, electronegativity, I'll just say En, increases. And as I go from top to bottom, electronegativity would decrease. Okay. Now, look here. We have the acidic hydrogen being bound to nitrogen in the first one, and then we have the acidic hydrogen being bound to oxygen in the second representation. And I say acidic hydrogen because that's what makes something an acid. It's all about protons, aka hydrogens. Okay. So I'm going to just say over here that I either have an HN bond or I have a HO bond. Now let's just say that I'm going to erase these. I'm going to just erase these and make like an electron cloud, technically, and I'm going to put 2 dots in there. Now, is this going to be equal sharing? Absolutely not, because nitrogen is more electronegative than hydrogen, and oxygen is more electronegative than hydrogen. So in both cases, it seems that these electrons are going to be pulled more closer to either nitrogen or oxygen, just like that. But now, maybe there's one that's pulling it even more closer to them. That comes from electronegativity. Nitrogen is over here, and oxygen is over here. And as you go from left to right, you increase your electronegativity. So which one out of these two is more electronegative? It would be oxygen, which means that this guy is more greedy. The more electronegative you are, the more greedy you are, and you want to pull those electrons more close to yourself. So these electrons are going to be even more pulled closer to oxygen, just like that. Now, in terms of the acidic hydrogen, which one do you think is more easily available to leave? Do you think it would be this hydrogen, where the electrons are kind of shared between H and N, or this hydrogen, where oxygen basically is taking all the electrons for itself and leaving hydrogen for nothing? It would be this hydrogen, because there's such a far difference between the electrons. Hydrogen is like, I don't even have these electrons, so I can leave. And that's how we know what the right structure is for any acid. The acidic hydrogen, and I will put that over here, the acidic hydrogen, H plus represents a proton, is always bound with the more electronegative atom. Because if that's the case, the more electronegative atom, in this case it's oxygen, is just super greedy. So the electrons are so close to that atom that the hydrogen is like, I don't even have those electrons, so I can just leave and join with a base. So off of that, we know that this one is going to be the correct structure. I'm just going to say that this one is correct, and this one is incorrect, because of just knowing what electronegativity is and how to apply it. But now let's do the formal charges. So I have O-N, double bond O. This has the 2 electrons. This has a H versus H-O-N, and then O. Okay. So I'm just going to go for similarities first. I see that this H is exactly the same as this H, because they both have a single bond and no lone electrons. So if I find out what the formal charge is for one hydrogen, I know it for the other one. So formal charge for this hydrogen is, I will use this formula, and you always start with the valence electrons, which is found on the periodic table. Hydrogen has 1 valence electron, So you'll say 1 minus, it's minus always the number of bonds, and then you minus again from how many dots there are around the atom. So for hydrogen, there's 1 bond, so I'll say minus 1, and then minus, is there any dots around this atom? No, so it's just 0. So 1 minus 0 is 0. That means that this hydrogen is neutral, and so is this. Now let's move on. I just realized that I didn't put lone electrons around this oxygen, and there you go. Oh, and I didn't put one around this one as well. Okay, so let's do this oxygen now. It seems like this one has 1 bond, and there's no other one that's the same as this oxygen, so let's just do this oxygen. Formal charge for oxygen in this case is, oxygen has 6 valence electrons, so that's 6 minus, there's 1 bond that's bound with that oxygen, so minus 1, minus the lone electrons, the dots, 1, 2, 3, 4, 5, and 6. So minus 6. And that should give you a negative 1. So this has a negative 1 charge. Okay, moving on. Let's do this nitrogen. Formal charge of the nitrogen is, nitrogen has 5 valence electrons, so we start with 5, minus, how many bonds does this nitrogen have? 1, 2, 3, 4. So minus 4, minus, is there any dots around this nitrogen? No, so minus 0. So this would be a positive 1. So that nitrogen has a plus 1 charge. And now let's do this oxygen right here. Formal charge of this oxygen is 6, because that was the formal charge for all oxygens. Sorry, that's the valence electrons for all oxygens. Minus number of bonds, 1, 2. Minus number of dots, 1, 2, 3, 4. And if we do the math, that is a 0. So that oxygen is neutral. And now if I just look here, this oxygen has 2 bonds and 2 lone pairs. And this oxygen, on the other drawing, has 2 bonds and 2 lone pairs. So if the one on the left was a 0, it was neutral, this has to also be neutral. And this oxygen has 2 bonds and 2 lone pairs. So that also is neutral. The only thing is now we just got to find out this formal charge of this nitrogen. Nitrogen has 5 valence electrons just like before. Minus, there was 3 bonds here and 2 dots. So that's 3 minus 2. So that's 0, and that's neutral. So once again, you could also find out which one is correct, because the more neutral atoms that are in a compound, the better the stability the atom is going to be, or the compound's going to be, and therefore that's the one that's correct. So I'm going to say over here, the less charges, the better. So in this one, on the right-hand side, there were all 0, which means that they're all neutral, right? Every atom is happy, as opposed to the one on the left, there was a negative 1 and a positive 1, and that's why this is also the correct answer. So you could either say it by electronegativity rules, or since they wanted the formal charges, we just did them anyway. But do you guys see how with chemistry you can get the correct answers in so many different ways? That's why I like chemistry. So if you don't know one way, you can kind of see it from a different perspective and you'll get the same correct answer. So it's not really all, memorizing formulas. All we got to do is just get these concepts down and apply them, and then you guys would be golden. So yeah, that's my little spiel. So thank you for tuning in. Hopefully this helped. Subscribe to the channel if you want to help us out, which I would really super appreciate that. We're heading towards 200 subscribers, so that's cool. I will see you guys all in the next question.